Hello, everyone. So today's Conference Monday. We are also starting our second unit of eighth grade. So last unit, the unit test that you guys just took was on rigid transformations, our translations, rotations, and reflections, and they were all focused on congruency. So you can use rigid transformations, you can use those three transformations to make congruent shapes. And we also talked about corresponding sides, corresponding angles, and angle relationships as well. What angles are corresponding, not corresponding, what angles are congruent and what angles are supplementary when we have parallel lines in a transversal. This unit continues to talk about transformations, but we are going to be looking at a fourth transformation now called a dilation. And the reason why dilation is in its own unit is because it does not keep a shape congruent. Dilations actually make similar shapes, not congruent shapes. So our learning goal for today is I know, we only have one learning goal for today. I know what it means for two figures to be similar. Now, you guys actually looked at similar figures a little bit in seventh grade, and really this unit's just adding on to what you guys already know. So when you make similar figures, you're actually using the transformation dilation. And so this is a transformation in which each point on a figure moves along a line and changes its distance from a fixed point. Now, what really is happening in this, a transformation in which each point on a figure moves along a line and changes its distance from a fixed point. So if I have a point and a shape, each point on that shape is going to move away from that fixed point. And because every single point is moving away from that other point, the shape itself is going to get bigger because the points are also moving away from each other. The shape could also get smaller if our fixed point and the distance of the points on the shape were actually to move closer to that point, then the shape would become smaller. So that goes into our facts and characteristics. So the fixed point is the center of dilation. So just like rotations had a center of rotation, dilations also have a center that you do have to define when talking about it. And all the original distances are multiplied by the same scale factor. So this is what you guys talked about in seventh grade. You guys talked about scale factors in seventh grade. You guys were given similar figures and had to identify what the scale factor was. So now we're going to be looking at dilations. We're going to actually be making the dilations when given a scale factor. So some examples here, if I have a fixed point, here's my fixed point. If I had a rectangle here, no, let's make it a trapezoid. Here is my trapezoid. All of the points I don't have an eraser here. I have to do this like a decent way that looks like the picture. I know if it's hard for me to draw and show, it's going to be difficult for you guys to draw and show as well. Um, so there's my fixed point instead. I moved it up a little bit. So we're looking for the straight line from each point in the shape and to the point, the fixed point itself. So pretend like those are nice, pretty straight lines going from the fixed point through each point in my trapezoid. And so now if I was to redraw my trapezoid, notice it's every single side got larger by approximately the same amount. Now, non-examples of a dilation would be if we had like a nice pretty square that got turned into an awkward rectangle. So notice that like the sides change differently. When you have a dilation, all of the sides change by the same amount. Every point on the shape is moving away. So dilations make similar shapes. If they are not um, being changed by the same scale factor, then they are not similar. They are not a dilation. And that goes into our next section here of similar figures. So similar figures are two figures. Two figures are similar if one can fit exactly over the other after rigid transformations and dilations. So we are not getting rid of our translations, rotations, and reflections. I don't want you guys to think, oh, we took that test, I can forget about it now. Because we're still going to be talking about translations, rotations, and reflections in this unit. We're just adding dilations into it. So you're still going to be writing those complete sentences describing what is happening. But this time, instead of describing these two shapes are congruent because I can rotate it 90 degrees to match it up, now we're going to say these two shapes are similar because I can rotate it 90 degrees and dilate it by a scale factor of 2 to match it up. Okay? So our facts and characteristics, if ABC is rotated around point B, I don't know how I feel about this facts and characteristics, and then dilated with center point O, then it will fit exactly over DEF. So this is really just an example. It's not like a facts and characteristics for every similar figure. This is going to be an example that we're going to do down here in this example. But to continue, this means they are similar. So again, if you can write a complete sentence using translations, rotations, or reflections and dilations, then it is a similar figure. Okay. So this one here we're going to have a small triangle labeled ABC. It says in our example up here, we rotated it around point B. So this point B is now going to be have um, this triangle rotated around it. So now this is A, this is C. And then here's my point O, that's my center of dilation. So here's going to be my new point E, D, F. So notice I rotated the triangle and then dilated the triangle. I rotated the triangle and then dilated the triangle. Again, my dilation non-examples would be the same here, but I'll just go ahead and give you another one. So if I had let's do a trapezoid again. If I had this trapezoid here, if I kept the top and the side length the same, but I kind of shortened these other ones, you could see like I can kind of rotate it, but this is not going to match like with the same scale factor. So I cannot dilate this to become this one. Um, what's weird is in my picture here. I see. Okay. Sorry, my picture for my example didn't make sense to me at first. Okay, so how can you check if two figures are similar? Two figures are similar if you can make them congruent through a dilation. So if you can use a dilation, if you can dilate one of the shapes, if you can make it smaller or larger, and then match it up and they are congruent, then it's similar figures. So we are going to continue to actually practice this throughout this week. So these are your notes, put these in your binders, and then you are going to move into a Desmos posted in Google Classroom. So go ahead, put these in your binders. And again, today is just the introduction. So I don't expect you guys to leave here today fully knowing how to create a dilation from scratch. We're just looking at the basics of it. So notice we have triangle A, B, and C. Here is point D. Triangles B and C are images of triangle A. So this is the original, this is the pre-image. These two are the image. It says, what do you notice? What do you wonder? So go ahead and fill this out for me. What do you notice? What do you wonder? Okay, one thing I want you guys to notice, if I was to take the straight line up here and drag a straight line through point D and then the top of point A, it's going to hit the top, not point A, triangle A, it's going to hit the top of each triangle B and C as well. If I was to continue to drag this point through the middle one on A, it's going to go through the middle one of B and C as well. And if I was to drag it through these ones here, it's going to hit those ones as well. So notice that each of the points on A, if I was to do a straight line multiplying its distance, it makes the points on B and C as well. We will not be drawing all of this out the whole unit. You guys will be getting shortcuts eventually. Okay, so here is screen 2. I want you to play around with each of these machines. Notice that the where your point is and the line that's going through it, okay? And draw something. Draw whatever you want. I'm gonna try to redo that heart here. Draw whatever you want. Does not matter what you draw. So here's machine 1. I'm gonna ask you, like, what is happening to the shape that you drew? What is happening to the shape that you drew? Okay, machine 2. Notice where your point is. Notice where the line's going. What is happening to the shape that you drew now? What is happening to the shape that you drew now? And how is this different than in machine 1? How is this different from machine 1? Even if I drew my shape over here, because I can draw it anywhere, how is this different? Okay. Moving on to machine 3. So now your point is here. The darker blue is the one that you are actually drawing. The light blue is what it's making. So what is happening to whatever you're drawing on machine 3? And machine 4, what is happening to your drawing on machine 4? What happened this time? And how is this one different from machine 3? How is this one different from machine 3? Okay. Here is a pre-image in a stretching machine. Trace the pre-image to see its image. So you're going to trace this using a straight line. And how would that image be different if point A was closer to the triangle? So go ahead and trace that. Okay. So if you trace this triangle, it should be in the straight line. We are tracing it straight down from point to point, then over here to this point, and then over here to this point. And you trace this one and it made this larger one. So how would the image be different if point A was closer to this triangle that you drew? How would how would this be different? Okay. So think about, would my big triangle, would the triangle that it recreated, would that be larger? Would that be smaller? Would that be in the same spot? Would it be in a different place? If point A was closer to this original triangle, how do you think the new triangle would be different? Okay, so slide 4, we are going to actually test whatever you said here. So we have the original triangle, we have the triangle that it traced, and we are going to move this point A around. So as we move point A, it is moving the new triangle. It is changing the new triangle. So when I move point A, what is happening to this new triangle? Is the size changing? Is the location changing? Or both? Is the size of this triangle changing, the location of this triangle changing, or both? If you said location, you are correct. The size is staying the same. The size of the new triangle has stayed the same, but moves to a different location. And that's because all we're doing is moving the center of dilation. We're not moving or changing the scale factor. So the scale factor has to do with the size. The center of dilation has to do with the location. Okay, so this shows some broken dilation machines. It says choose one image that is not a dilation. In other words, it could not have been created using a stretching machine. So I will say that there is one that is a dilation. Three are not. You just have to choose one of the three that are not, but be ready to explain. Okay, so if you chose B, C, or D, you are correct that these ones are not a dilation. So I want you to explain why these ones are not. A is a dilation. Notice that the lines are nice, perfect straight lines through the points. Okay, so B, C, and D are broken machines. What is wrong with B, C, or D, whichever one you chose? Okay, if you said B, hopefully it's because you noticed that these aren't didn't give us straight lines all the way through. This line and this line, the bottom 2 points, the line that it goes through is not a straight line. It kind of has a break in it, which makes our rectangle kind of skinnier than it should have been because it should have been a square. C, if you said C, well, notice that one of these lines doesn't even go, many of these lines don't even go through the actual points on the new shape down here. And it took us from a hexagon down to a pentagon. So these two aren't even the same shape. And if you said D, notice that it's because these points aren't the same, being multiplied by the same distance. So this point and this point to this point looks like it's being multiplied by about 1.5. This from this point to this point, this should be longer. Okay. Again, it's not even the same shape. This is a rectangle, a parallelogram. This is not. Okay, so keeping that in mind, keeping what we've done in the last few slides, move point A and point C. So point A, we know changes the location. Point C is going to change our scale factor, and it's going to move us closer, further and closer from point A. Okay, so use A and C to try and figure out if each of these are possible. Can you make the image smaller than the pre-image? Can you make it smaller than this original one? Can you make the image the same size as the pre-image but in a different location? So can it be the same size as this one? Can it be congruent but not right on top of it? Make the distance between A and B twice the distance between B and C. So it wants A and B to be 2 times the distance from B to C. And then can you make A, B, and C form a triangle? Can you make point A, point B, and point C form a triangle? Man, the amount of times I've had to pause this recording today. Okay, so If you said make the image smaller than the pre-image, you are correct. I can move C and it is now smaller. I can keep, the closer I get it to point A, the smaller it is. Okay. If you said make the image the same size as the pre-image but in a different location, that is not possible. Because if I make it the same size, my moving point C to a scale factor of 1, meaning it's the exact same size, it cannot be moved away from the original triangle. It can be the same size, but you can't move it away, not without a translation or rotation or reflection. So if you want it to be the same size as the pre-image, but in a different location, you have to use translations, rotations, or reflections. And then this one says make the distance between A and B twice the distance as B and C. You are correct. You would just have to make it smaller. So um, it would have to be C would have to be halfway between A and B. C would have to be halfway between A and B. And then if you said make points A, B, and C form a triangle, that is also not possible because dilations keep our points in a straight line. So A, B, and C will always be a straight line. Your center of dilation is A. Point B is the point on the original triangle, and point C is the corresponding point on the new triangle. Those will always be a straight line. Okay, this one here, I want you guys to do on your own. Which figure could be a dilation of figure A? B, C, both, or neither? Go ahead and answer this on your own and explain your thinking. Which one could be a dilation of figure A? Number 8 says describe how dilations work. Use the sketch tool if it helps. So you can use the sketch tool. You can use the notes that we did beforehand. Explain, describe how a dilation works. When I dilate a shape, what is happening to the shape? How does the shape change? What's happening? Okay, slide 9, select all the figures that could be a dilation of figure A. So think about that kind of dilation machine with the point. Which one of these could be a dilation of A, and explain your thinking? And then tell me how you felt about the lesson today. Okay? If you have any questions, please let me know.